carefully. I don't know which one I'm doing here, question mark. What are you saying? What do you think, Dave, I should use? And we'll try it. That's what we'll do. Let's try one, we'll see if it works. What do you think? That one or that one? He's going to go with that. All right, let's check it. Don't worry, because David, if it doesn't work, you're not going to go with that one. We're going to test it out. Let's see if this works. What's the very first number we're plugging in there? 0. What's -1 to the 0 power? Positive. So that means this first term would have to be positive. Is it? Nice, cool. All right. Then the next number we're plugging in is a what? A 1. And when you plug in that 1, this becomes what? Negative, is that true? I think you got it. So what we're saying is that when he nailed this, the first term was positive, the second was negative, this is going to work. But if you do like every problem out of this section, I know a lot of you will practice all my practice problems, you'll notice sometimes it might start with a negative and then go to a positive. And you go, well, how do I make that work? You'll just use this. Does that make sense? So you actually just, it doesn't take much, you can just play with it and study it. You can play with it. All right. -1 to the 0 power should be a positive number. It works, right? But if that was negative, I would have done the -1 to the n plus 1.
So if it started off first number was negative.
If it was negative, and I want you to see this. If this was a negative right here, I'll erase it. Then you'd be like, crap. I plug in a 0, it's coming positive. But what would work? Check it out. If you had an n plus 1, when you plug in a 0, you get -1 to the 0 plus 1, which is -1 to the first. Okay, I'll go back and put it back. So you got it. Let me get back to the end. Whoop, get this out of the way. And this is working well, right? Notice I was looking at this. Connor.
So like, isn't that actually the third term, not the second?
Great question. Because you and I did this to get it set up, I want your eyes to focus on this.
Okay.
I love your question, because that can be confusing. You start looking up there. So I'm going to put my eyes. Let me put a set of eyes here. Nose. Because we did all this, and I'm looking at this. That's what we're looking at. We did this to get the thing set up, but those zeros were tricky. Wiping these two entire terms out of there, and you and I are trying to present a formula for this.
Okay.
And I think if we tried it from this, Connor, it would have bugged us. Because we would have been like, what's going on? How can it go 1, 0, -1, 0? It's like, let those zeros go away, we're just dealing with that. Alternate zeros. So, and this is what we studied to come up with this. Looking back, does it look good? Could you check it? Nice. Hey, great job with that. Number 17, I won't do it, that's one of your practice problems. It's cosine, it's centered at pi. So see how it plays out. You might get a, if it comes up with the, doing like a 1, 3, 5, 7, then use the, not a 2n power, but do a 2n plus 1. Sound good? Hey, are we done with the problem? Oh, goodness. What do we got to do now? Yeah, so that's why you go, our next test, it's not like we can put 10 problems on the test, because one problem seems to take a while. But hey, we're patient. We'll get this. That was the hard part. We got it. This is what we're going to do the radius of convergence. We're going to do the ratio test on. Super job with this one. There's the answer letter right. I'll get my eyes out of the way so it's not a little confusing. But Connor, that was a really good question. That was our scratch work, right?
Right.
But then we studied this. You could have done another one. Keep in mind, everyone, I just went out to like the minimum. I think with sine and cosine, you want to go out about those 0, 1, 2, 3, 4. But you could have kept going. Maybe that helps you see the pattern more clearly. All right. Let's find the associated radius of convergence. All right, then n goes to infinity. -1 to the what? Does everyone even know what's going to happen to that -1 to the n plus 1? You got an absolute value bar around it. What's going to happen to it? Yeah, so if you just want to skip that, you can. You're like, that's 1. I do have to do this x minus pi over 2 to the 2n plus 1. Is that right? Thank you. Look at this. That's where we got to be careful. How do I write that? It's 2 substitute n plus 1 for the n, which makes it a what? it's gonna be a 2 substituting n plus 1. Which means that power will now be 2n plus 2. You wanna do that? Nice. I know that's weird. Does anyone see that? That's 2 times multiple n plus 1. That parentheses, the quantity n plus 1. It's really a substitution when we do this ratio test. I am substituting an n plus 1 for that n, but the 2 has to get distributed. All right, what else? We got a 2n, so now what do I have? 2 times, oh gosh, don't let this bug you. Is that right? No, 2n plus 2 factorial?
Yes.
Just so it doesn't bug you, I got 2, substitute n plus 1 for the n, then a factorial. But you're probably going to write this as what? 2n plus 2 factorial. I wanted to write it that way first. What do I write it that? Very good. I'll write it. 2, this looks better, doesn't it? 2n plus 2 factorial. Okay. What do I got to divide? I have to put a dot and divide the ace of it. Let's divide this, which means everything what? Flips. All right, put that up here. What else? Maybe one of the n? X minus power 2 to the n. There's my bars. Less than what? Always less than 1 for conversions, true? Now some of you do 2 or 3 things at once. Let's talk about these -1 to the n's. What's going to happen to those? There's absolute value bars wrong. That's just 1, right? Get rid of all of it. I mean, you could have left it -1, but absolute value -1 is just a 1. 1, so you're going. What's that going to become? That will become x minus 2 to the power, x minus power 2 to the 2n times an x minus power 2.
We wrote the
Square, right?
bit wrong. It's x minus pi over 2 over 2n.
Oh, right here, yep. There's a 2n right there. All right. So what do we have now? Limit. N approaches infinity. X minus power 2 to the 2n times x minus power 2 to the 2. You got a 2n factorial. And this is all over 2n plus 2 factorial. X minus power 2 to the 2n. Take the bars off, everything's positive. After this part, what cancels?
Minus pi over 2
You're gone. You're gone. Okay, you gotta help me simplify this. We know this is just gonna put the x minus pi over 2 squared out in front, right? Okay, we get it. We're just gonna put that thing out in front of the limit. But how do I simplify 2n factorial over 2n plus 2 factorial? Let's check that out. All right, how am I gonna deal with this?
1 over 2n plus 2 times 2n plus 1.
That'll be in the denominator. Be very good. So just to think about this, this is 2n. What's 1 less than that? 2n minus a 1, right? You agree? All right, what will this be? You got a 2n plus 2. What's 1 less than that?
2n plus 1.
2n plus 1. What's 1 less than that? 2n, da 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 da, etc. What cancels? Everything cancels except for what's sitting in the bottom? 2n plus 2, 2n plus 1. So that's what this is about. All that, let me box it off, will become 1 over 2n plus 2, 2n plus 1. We'll stick this out in front of the limit, and then we're going to find that limit and see when it's less than 1. And I got plenty of room right here to do it. So I'm going to write it right down. You got the absolute value bar. X minus pi over 2 squared. That's coming outside my limit. I want that to be our focus. We're trying to find the radius of convergence for that letter x right there. Put that up in front. Now I gotta evaluate the limit as n approaches infinity of, what's the only thing left over? And I don't think you gotta FOIL that out, everyone. I think you're gonna know the answer.
0, 0.
We got another 0. That's going towards 0. So when this is a 0, we don't say there's no solution. It's the complete opposite. What's the radius of convergence? Infinity. Interesting. Look at the Maclaurin series for sine of x. What's the radius of convergence? Infinity. That's what I mean when I think it's good to know some of these because you can expect to get a very similar solution. But when this is going to 0, you go, what about this? Well, 0 times the absolute value of x minus power over 2 squared is always going to be less than 1 for every x value. So what's the radius? Infinity. That means all real. Which is so cool. So now we can use a calculator, program this into a calculator, into a computer, and say, this power series right here will represent the function sine of x centered at pi over 2. Cool. Or you can send it at a equals 0. Nice. Hey, when this Maclaurin series, it's the same thing. The only difference is, what do you put for the a values? 0. So they look cleaner because you're just going x to the 0, x to the 1, x to the 2, x to the third. I mean, they look a lot better. And then you're evaluating everything at zeros. It's usually pretty easy with an e, because e to the 0 is 1. But it gets a little weird with sines and cosines because of sine of 0 is 0, cosine of 0 is 1, we get it. But it does make it alternate. That's why you get these alternating series with sine and cosine. Would you look at that from Maclaurin? I mean, you could do that. You go, hey, tonight I'm gonna prove the first 3 tonight for practice. You could do that. Prove that these are true. It's a good exercise. But do you notice? Look at sine and cosine carefully. Do you have this sheet from Maclaurin series? Look at them carefully. What does both sine and cosine have? The alternating -1 to the n. Yeah. One of them has a 2n plus 1 over 2n plus 1 factorial. The other one has 2n over 2n factorial. I mean, just some cool stuff here. Can I raise? Yeah. Love it. Great job. Dave, thanks again for right there, because that could really throw me off when I'm trying to simplify. That was a 2n right there. Not just an n. Everything comes out nicely. Hey, again, what if this came out to be like a half? Then you just multiply 1. A 2 on both sides. But similar to, I noticed on the Maclaurin series, EDX had a radius of infinity. The previous problem had radius of infinity. Centered at, it was what? Centered at a equal to 2? This problem, function sine of x is centered at a equal to pi over 2 for a Taylor series. The sine of x on here for the Maclaurin series has a radius of infinity as well. So that can be helpful because we're getting very similar answers, right? Nice. I love it. Everyone done copying? Good. All right. So now let's apply this. Let's apply. You might say, hey, I want to do a Taylor series. That's a equal to 0, which we call a Maclaurin series. Of course you could. You'll find those easier. I'll work that out. Can you find a Maclaurin series for e dx? That means you're not going to be given the a value. Where's it centered?
0, 0.
Well, wipe this out. What's going here? Zeros. I think you're going to love this. What goes here? EDX? What's their EDX? What's their VDX? What's their VDX? Okay, more fun. What's e to the 0?
1.
Well, what we're doing right now, we're proving that first formula, it's the second formula in McLaurin series. That's the one with z to 0. G of McLaurin series, but if it's a McLaurin series, what's this number? A is what? Oh, A is 0. That's what this means. So when, please make a note, this word means it's centered at A equals 0. So this formula does get simplified a little bit. What can I put there? What value? Plug in 0, and then what happens to this? This shrinks. Now it's just what? Right? X minus 0 to the n, that's why I didn't want to write a whole new formula for you. Just say Maclaurin series, it's centered at A equals 0. It turns into this, right? Evaluate all n derivatives at 0. There they are. All these nice ones. Oh, that negative, I'll get it all. So you're quiet. You're the best. I don't let that mark on there. That's what I get when I leave these tables up, right? I mean, thanks for seeing that. Get that negative out of the way. Make sure I get all these other slashes out of the way in there. These are all positive ones. All right, try it. Box x to the 0 over 0 factorial. Box x to the 1 over 1 factorial. Box x to the 2 over 2 factorial. That might be far enough. Dot, dot, dot. What's going in those boxes? Oh, a bunch of 1s. And you're proving what the actual Maclaurin series is for the function e of x. So what is e of x equal to? Can you hit it in segment notation, Owen? Whoop, whoop, whoop. And equals 0. That's a 1. Do I have to even write the 1? X to the n over. Isn't that cool? We're saying that when this is e to the x. And if you want to check it, we won't do it now. The radius of convergence, guess what it is? It's like our first problem of that. Radius is infinity. So today we're learning that this power series right here, Taylor series, x to the n over n factorial, because it is a power series, is equivalent to e to the x. They are equivalent. I can say this, I can write this, I can say you're equal to e to the x. I can program now this into a computer. I can actually program this so people don't have to carry around like in the 1960s, 70s, and 80s textbooks and look in the back of the book to estimate e to the second power and e to the third. You follow me? I need a table for that. I don't need a slide rule. Let this be the program. And then you go, we talk about, how accurate you have to be in terms of decimal places, which we're going to do now. You're not raised? Okay, cool, that was great. So this is really just a proof of the first problem. If you want, or the second one on the sheet. If you want to do more, play around with it. Like even say, hey, I'm going to show that cosine of x is equal to this. And I do, I think it's good to know these. Maybe not all of them, but how about e to the x, cosine of x, sine of x, and definitely the 1 over 1 minus x, the first one. It's good to know this Maclaurin series. So this was called a Maclaurin series, right? It only means a equals 0. So that word Maclaurin series, as I'm erasing, a Maclaurin series is a Taylor series centered where? At 0. That's all. Alright, so now I get to erase that. And we're going to try one. Now, again, I keep referencing this table of important Maclaurin series. I'm saying you don't, it's not mandatory, it's not required that you memorize these. So now I'm going to give you a problem where I actually give you one of these, but you're going to use it to work a problem. So, this is like number 47 in the textbook. All right. Given this information, given that sine of x is equal to, you can make sure I write this Taylor series properly, n equals 0 to infinity, negative 1 to the m, x to the 2m plus 1 over 2m plus 1 factorial. I'll let you all check it. Did I write that properly? Check it over, that Maclaurin series. Is that right? I know you missed something. I'm doing it from memory. Is that sine of x? Yeah. Okay, good. But that's what I mean. I know sine, I know cosine, I know e dx, the x to the nth over n factorial. How hard is it to remember that? But given this, we're saying this is given to you. Right, so I'll put a comma. And its radius of convergence is infinity, right? We don't have to write that. They want you to find the indefinite integral. Find the indefinite integral for I just changed it 47 a little bit. X cubed sine of x cubed dx.